Yes, I messaged him. Okay, so cool. Yep. Okay. All right. So let's get started. Thanks for everybody for being here in person and on Zoom. And happy April Fool's Day. I don't know about you all, but I am shocked that it's April already. It's making me nervous a little bit. That the semester is going so fast. So we have a presenter today, and we also have Dr. Pine, who's on Zoom, who's going to do the introduction. So Dr. Pine, I'm just going to turn it right over to you. Don't worry about that. I'll take care of that.
All right, thanks, Allison. So thank you everybody for joining us this afternoon for Matt's seminar. Matt has been an incredibly outstanding PhD student, and he successfully defended his dissertation just a couple of weeks ago. Matt came to us with a very diverse skill set, and as one of the most technically proficient students that I've worked with from a programming and analytical perspective, we were able to work with Matt and his committee and co-advisor Julian Martin to capture these skills and put them to work as part of the Lone Cabbage Reef Restoration project that's been ongoing in the Big Bend region near Cedar Key. And Matt's helped us to really shed new insight into the role and functional aspects of reef restoration related to water quality. And I'm excited he's going to share this framework with you today. At the same time, his work has broader implications besides just related to Lone Cabbage Reef, and I think will be critical to informing oyster restoration efforts in Florida and throughout the Gulf of Mexico region. So Matt, we appreciate all your contributions, not only to the Lone Cabbage Project, but to SNRE and to the University of Florida. So thank you for sharing your work with us today as part of your exit seminar.
All righty, thanks, Bill. So yeah, my dissertation is titled Quantitative Frameworks for Oyster Reef Restoration or Oyster Reef Monitoring and Restoration in the Big Bend of Florida. So I guess we'll just get right into it, if this will go. So globally, oyster reefs have been in decline, with a majority of areas such as the eastern and western coast of the United States having relatively poor to or functionally extinct oyster reefs. Primarily in the Gulf of Mexico is one of the few areas we have fair oyster reefs in North America, although these are also on the decline. Looking at the western coast of Florida, so that part of Florida on the Gulf of Mexico, we can see that around 1990, 2000, we start to see a dip in the overall landings, which is the harvest from these different oyster reefs. And so the notice of these reductions in harvest kind of led to people taking special interest within the west coast of Florida. One area in particular is Swanee Sound. And so Swanee Sound is composed of 4 major oyster reefs: Horseshoe Beach, Lone Cabbage Reef, Cedar Key, and Corrigan's Reef. Some work within the area showed that from 2010 to 2018, at all of these different reefs, intertidal, nearshore, and offshore populations were in decline. And so one area of specific importance is that Lone Cabbage Reef. And so looking at from the 1995 images we have to 2010, you can see a severe reduction in the overall oyster population on that reef. And in fact, the reduction in this population was noticed by oystermen within the area, which led to some overall hypotheses about why potentially we were seeing these losses. To test these hypotheses, first a pilot project was introduced within the area. This was relatively small scale, only about 360 cubic meters over 85 meters of reef length. What they found from this pilot project, that the placement of durable substrate did result in increase in mean oyster density on these sites, indicating that it is substrate limited and not spat limited. We just need a physical substrate for the oysters to land on to form these populations. Additionally, what they found was that salinity field measurements confirmed that salinity difference existed between the landward and the seaward sides of the Lone Cabbage Reef. Basically, that the physical reef structure may have some part in modulating overall freshwater intake within the system, which could result in lower salinity conditions on the landward side of the reef. Following this pilot project, a larger scale project was introduced, around 13,000 cubic meters as compared to the 300, and over 5 kilometers of overall reef length as compared to that 85 meters. So a lot bigger of a project. The overall goals of this project was first to see the colonization and persistence of oyster populations on these restored sites. And the second objective was to look for evidence of freshwater detention provided by restored reefs at these larger spatial scales. And so my dissertation first kind of focuses on this second objective, which leads us into the first chapter. And so looking at the overall pilot project data, we have 3 high frequency sensor pairs, LC1, 2, and 3. These were deployed from 2013 to 2015 within the region and collected data every 15 minutes. Comparatively, the lone cabbage reef restoration was from 2017 to 2023, so a much longer time series of data. It followed a similar structure with three high-frequency sensor pairs at the northern, middle, and southern ends of the restored reefs, and this collected data on an hourly timescale. Important to note is that that figure I previously showed you, kind of pointing out the lower landward salinities, was on a daily timescale, so they had aggregated their data. Here, I aggregate everything to an hourly timescale for the pilot project just to match up with the lone cabbage reef restoration. And so here's just an idea of what that looks like. It's really noisy. Don't look too much into it. But I said it was from 2013 to 2015. Realistically, it's the tail end, so that December of 2013 to about mid of 2015. And there are some data gaps across different sensors, and primarily one in the fall of 2014. Compared to the lone cabbage reef restoration, much longer time series, no major data gaps across all of the sensors except for 2020 during the pandemic. And so to look at the overall idea of freshwater detention, it might help if I explain what that is. So as defined by earlier work in the area, freshwater detention is the maintenance of consistently lower salinities on the landward side of the reefs relative to the seaward sides. In earlier work, they used just a simple assessment, so I've recreated that here. And that was just these one-to-one lines. So looking at the ratio of the salinities on the seaward to the landward side. If these values are less than 1, salinity is higher on the landward side. If they're equal, it's equal on both sides. And if it's greater than 1, then salinity is lower on the landward side. And if we see consistent ratios greater than 1, then that would indicate evidence of freshwater detention. And so thinking about the hypotheses for these two different data sets, for the pilot project, we would expect the same patterns as work earlier in the region. So here I'm reanalyzing this daily data at an hourly timescale. And so just looking at that, what we can find is that we see at this LC1 sensor, we see a majority of the points are consistently above this dashed line, which is our one-to-one line, indicating some evidence of freshwater detention. And then as we move south in the reef, away from the river mouth, these points become more evenly distributed around this one-to-one line, indicating that there's no real evidence of consistently lower salinities on the landward side. Thinking about the lone cabbage reef restoration, we would expect to find consistently lower salinities at water quality 1 as compared to water quality 6. That's because it's in that northern end of the reef close to the river mouth. Additionally, we would expect this amount of freshwater detention evidence to be higher, considering it is closer to the river mouth as compared to LC1. And then we would expect to find no pattern of consistently lower salinities at water quality 2.5 and 3.4 because they're lower than the LC3 sensor, which we found no evidence for previously. So looking at those, what we can see is that there's a lot more data points, right? Because it was a much longer time series. But at this water quality 1.6 pair, we can see that there are a significant amount of points above this one-to-one line, indicating some evidence for freshwater detention, and that as we move down the reef, this disappears, and we get a much more evenly distribution of points around the line. So overall, for our hypotheses, for the pilot project, we did see the same patterns at an hourly timescale as we did at a daily timescale. And additionally, for the lone cabbage reef restoration, the only hypothesis that we saw conflicting information for was that the water quality 1.6 has stronger effects of freshwater detention than LC1. And so that kind of led to a question of, okay, what exactly could be driving these observations? Is it environmental conditions? Salinity is a very complex process within estuaries, really defined by the hydrodynamics of the system. So just kind of looking at comparisons of values on one side of the reef to the other isn't really that scientific. And so are there some physical drivers that are driving these salinity patterns, and how do those vary over space? River discharge has been shown by other work in the area to be linked to this discharge or linked to this salinity observations. So that's one that we wanted to keep in mind, as well as some others I'll talk about in a second. Additionally, for the pilot project, those sensors were much closer to the reef. And so is there some interaction between the physical reef structure and the salinity we're seeing at a localized level as compared to the lone cabbage reef restoration sensors, which were placed further off reef? Or is it some combination of the two? And so the overall idea was, okay, we have all this physical data for Swanee Sound collected from various sources. Can we all link this together through some quantitative framework to try and see how these different variables are driving? So we have our salinity observations over here. And what we have our discharge information, the tide height, and then our wind speed and direction. And so looking at just the distributions of these variables during these time periods, we can see that our tide height, wind in the X, wind in the Y direction are relatively similar between the two time periods, meaning that we observe similar values across all of our sensors when we compare the two. Where we do see differences are in the temperature and discharge. Temperature, we do see a gap of these intermediate temperatures for the pilot project, which is really just indicative of missing that fall period. We get summer depth values, we get winter values. There's nothing really crazy going on there. And then for the discharge, we actually do see consistently higher discharge during our pilot project time period as compared to the lone cabbage reef restoration. And so given the fact that we know discharge is linked to salinity in a strong way, it was important to look further into this discharge. And so here I have just the overall heat map of the discharge levels from the pilot project and the lone cabbage reef restoration. If the cell is colored white, it's within plus or minus 10% of the historical median value. Blue indicates higher discharge values compared to the historical values, and red indicates lower. So we can see for the pilot project, we had consistently higher discharge values during the time period of collection. And then during the lone cabbage reef restoration, we had a mix of both lower and higher discharge. And so that's just one thing to watch out for as we continue through our modeling process. So the overall model I chose to link the salinity in these physical drivers was a random forest model. Here you can see all the information on it. The main things to point out is that I did use a model ensemble of 25 runs to account for the impact of starting conditions and use minimum range standardized weighted average to create the ensemble. Essentially, this chooses models that explain the data well and gives them a high weight, and models that explain the data poorly get a low weight. And then I evaluated overall variable importance using permutations, and I'll talk about that later. And I used 100 permutations per predictor. So graphically, what that looks like is, it might be a little hard to see. Can I zoom in? No. Okay. So what you can see is that the black line is actually our observed salinity, and that gray line is our model fit. So overall, we have really good fit here for the pilot project, and then consider looking at the fit for the lone cabbage reef restoration. We can see that we don't fit as well, and we miss a lot of these peak values, but overall the fit seems pretty good. And then looking at the overall statistics, we can see we get an R-square of about 0.95 for the pilot project, and then 0.88 for the lone cabbage reef restoration, indicating really good model fit, right? So the idea is, if, okay, we have this random forest model that fits our data, can we see how each of the variables that contribute to that model impact our model performance? And we can use that as kind of looking at the statistical significance of each of our covariates within our model. It's not the same, but it kind of gives us an idea of what is driving our model performance. And so looking at the pilot restoration, I use mean absolute error percent difference. All you need to know here is that the taller the bar, the more important the variable was, right? We can talk about later if you want to know all the technical stuff. But here we can find that discharge across all of our different sensors was the highest contributor to model performance, followed by temperature, and then tide height, and then wind X and wind Y, depending on the sensor. Indicating that for the pilot project, our model performance was heavily tied to discharge values. Additionally, we can find on the seaward side that our wind in the Y was more important than our wind in the X. And on our landward side, our wind in the X was more important than our wind in the Y, indicating something about the physical structure and the interaction between wind and salinity on that level. On the lone cabbage reef restoration, you can see we see similar patterns with discharge and temperature being the highest, although the magnitude of this importance is much lower, right? There's still a heavy tie to discharge. However, because we have a much larger parameter space during this, I think that may have contributed to the overall discharge patterns here. Additionally, we see tide height varying drastically between the different sensors, which may be more of a factor of bathymetry within the area as opposed to tide height varying over space. Additionally, we see wind X and wind Y are important, with wind Y being more important than wind X for all of the sensors, and it's pretty consistent. These sensors were placed further off reef, so it kind of makes sense that we wouldn't necessarily see different impacts of wind on these sensors that are basically in open water. And finally, just comparing the two, we can see that the pilot restoration is much more sensitive to these discharge and temperature values as opposed to the lone cabbage reef restoration, which indicates that there is some importance of discharge here, and potentially the discharge patterns during the pilot restoration could be what's driving our salinity observations and could be related to that increased freshwater detention that we saw. However, this isn't enough evidence to truly state that, and more work is going to be needed to investigate the role of discharge with salinity with these restored reefs. All righty, get a drink. So moving on from that first chapter, following analyzing the monitoring data, the next question I had was, well, how could we go about restoration in the future, right? Lone Cabbage Reef restoration provides a framework for performing restoration in the area following an adaptive management protocol. But the question with restoration isn't how we should do it. It's necessarily how do we identify sites for future restoration efforts. Lone Cabbage Reef restoration used historical extent, and is that something we should do, or are there other options available? And so looking at the overall historical extent, you can see based on the mid-1800s extent to 2001, that Great Swanee Reef was heavily degraded over time. Lone Cabbage Reef did exist, but as we know, moving into the 2010s, we saw declines there. However, restoration has occurred on Lone Cabbage Reef, so it leaves the question of should we restore Great Swanee Reef, or are there other areas we should be considering for restoration? And so here, if we just look at Lower Swanee Sound to date, we have the Lone Cabbage Reef restoration restored reef here, as well as these wild reefs kind of interladen in the coastline. And so for the purpose of my dissertation, I focused on these areas for consideration for future restoration actions, kind of looking at alternative ways to historical extent. And so, so this is from my qualifying exam. And at the time, my committee had me make a conceptual-based model for oyster reefs and how that worked. And at the time, I thought it was really brutal and really mean. And I didn't like my committee at the time. But as I worked through my dissertation, I found that this was actually a really good tool for understanding how restoration plays a role in oyster reef systems and helped me kind of guide the rest of my dissertation. And so I recreated this in a much more digestible format that I'll walk through really quickly, just so you guys get an idea of where I'm coming from. And so we consider the overall habitat for oyster reefs. It's made of just rocky substrate. This is just some physical structure which oyster spat can land on and start to grow the populations. At the different habitat, at the different reefs, we'll have a juvenile oyster population, oyster and adult oysters. And in fact, oysters are ontogenic engineers, which essentially means they help contribute to their own habitat. And so the adult or juvenile oysters contribute to this dead oyster stock, which then combines with the overall substrate there and makes an overall habitat matrix. And so the process, these are all the demographic processes driving these different parts of the population. And of course, we can have adult oysters removed by harvest, and the habitat matrix can be degraded by erosion and climatic events. And in reality, we're not necessarily dealing with an individual large oyster population. It's more of a meta population where we have each of these individual reefs with their own habitat and their own population dynamics, and they're all connected through complex larval dispersal dynamics within the system. And so the question is, where does restoration fit into this? And so if we consider just a spot that doesn't have any suitable substrate, right? The process of restoration is placing that substrate there. We then hope through some larval dispersal that we can have spat land on these restored sites and create a juvenile oyster stock. That stock can survive and grow and then eventually form the overall population dynamics. And so when we're considering our restoration outcomes, what we're really concerned with is that first, our restored site becomes occupied, right? This site is there, we put rock there, we want oysters to come to it. And they do that through larval dispersal, larval transport. And then once individuals are at these sites, the population persists. And this is governed by the population dynamics. And so anyone who's dealt with these types of modeling, you know that modeling each individual demographic process here is very complicated and requires a lot of data and a lot of work to collect that data. And so the goal of my dissertation was to look at alternative methods that could go past, say, an integrated population model for modeling the oyster populations. And that's what gets into my second chapter. And so here I use habitat suitability index models. For those of you unfamiliar, these are spatially explicit decision support models that identify areas with the highest probable habitat quality. The idea is that if we have high habitat quality, we should have high abundance. If we have good habitat quality, these demographic processes should occur at rates that allow population to persist. There are some limitations to these models, of course, mainly that you need a good understanding of the habitat requirements for our species of interest so that you can identify sites with good habitat. Additionally, you need spatially explicit habitat observations. You can do this through exhaustive sampling, which can be very costly, and depending on what you're sampling for, it can be impossible. And so generally, what we do is point sampling and use some type of spatial interpolation to fill in the gaps, either through hydrological modeling or statistical modeling in the case of Oyster Reef restoration. The problem with this spatial interpolation is that it introduces error within the process. Of these sites where we don't sample, we're making an estimate of what the potential habitat value is, but we don't necessarily know it offhand. And depending on the spatial distribution of our sampling efforts, we may end up with areas of higher error and places that are sampled less frequently. And so the objectives of this chapter was to develop a framework to account for this uncertainty in habitat suitability metrics within the HSI model formulation, and then look at how this inclusion of uncertainty affects our decision process. And so just the overall standard HSI modeling process is first we spatially interpolate our suitability metrics. Here I use just salinity and temperature. On the right, you can see for 1 month, January 1997, here's just the distribution of salinity and temperature sampling efforts. I then use just ordinary kriging in my case to spatially interpolate. I do this at a 1 hectare scale, which fit our data best. And then you can see the kriging standard error with these darker blue colors indicating higher error in areas that weren't necessarily sampled. You then need to transform these into suitability values. This is generally done with suitability functions. These are based off of physiological responses of your target species within a laboratory setting. So looking at growth, reproduction, mortality in a laboratory setting, and how across these different gradients, in my case, salinity and temperature, the adult and juvenile oysters respond. Finally, you take these spatially interpolated values, transform them, and then average them across time at each site. Here's what that ends up looking like for Swanee Sound. So you can see for adult and juvenile salinity, we have this contour line at the northern end, indicating that as we move away from the river mouths, we end up with higher suitability for salinity. Additionally, for adult and juvenile temperature, it's fairly homogeneous across the entire system, with suitable habitat for juveniles and highly suitable for adults. You then average all of these different indices into one large index to give you the overall suitability map for your area. Here's what that looks like here. Once again, you see that contour line. Moving away from the river mouth, we end up with more suitable habitat. So the question is, where do we introduce uncertainty in this process, right? I chose to do it in the second box where we transform individual suitability metrics to suitability values. And I'll briefly walk through how I did that. So I used the Monte Carlo simulation. You can think about these Kriged estimates of being parameters from a Gaussian distribution. I then transform them to log normal to bound at 0 because our salinity and temperature can't be below 0. However, you could choose whatever distribution you want. Then you take random draws from that distribution to obtain an empirically derived probability density function. You discretize this PDF and then use that to calculate an expected value for HSI. Essentially, for values that have, for sites that have very little model error, you'll end up with the same value. For sites that have large model error, you may shift it higher or lower depending on the overall standard error around our model estimate. Mathematically, here's what that looks like for anyone who's more mathematically inclined. And so here's what it ends up looking like for the Monte Carlo simulations. You'll note we see the same patterns for adult and juvenile salinity as well as adult and juvenile temperature. Similarly, when we combine them all together, we end up with a very similar plot, which at this point I was very concerned that I had wasted all of my time. But you can see that they have the contour here with increased suitability as we move down. And so the idea was, well, if it doesn't look like there's very many differences, how can we look at that? And a simple one is just a raster subtraction. So what I did is I took the standard methodology and subtracted the Monte Carlo simulation to see at each site how we're seeing differences and how that varies across the estuary. For adult and juvenile temperature, we get values of almost 0, indicating that for at least those, we don't really have uncertainty that impacts our HSI calculations. For adult and juvenile salinity, we see that at the northern end of the estuary, we have the standard methodology has lower HSI values than the Monte Carlo. And as we move down the estuary, for the adult, it kind of equalizes. For the juvenile, we see lower for the standard and then higher for the standard at the very bottom, indicating that we are seeing some slight differences between the two frameworks. Additionally, when we combine them all together and compare, we can basically see that in the northern end of the estuary, we see consistently lower HSI values when we use the standard methodology as compared to the Monte Carlo simulation. As we move down the estuary, these basically become 0. So we're really just seeing differences in this northern part. However, there are small differences in the lower areas. And so we do see differences. That's great. However, are these actually impactful, right? Do we whenever we utilize these HSI values for site selection procedures, does it actually change our decision-making process? So a standard decision problem for using HSIs is that we just choose sites that maximize our HSI. We have all of our sites in a list, and we look at the ones that have the highest values and say, we'll choose those. This fails to account for the connectivity of our newly restored sites to the overall meta population. As I mentioned, we need these sites to actually get new individuals for the population dynamics to start. So this could result in the failure to colonize these new sites. And so what we can do is reframe our decision problem as a maximum set coverage problem and incorporate budget and spatial constraints to make sure that we're connecting these newly restored sites to the overall meta population. So to do that, I first looked at where are oysters actually in the area, right? And so looking at the Oyster Integrated Mapping and Monitoring Program, here you can see all of the point observations of oysters. I just changed them to a raster to match up with the spatial resolution of our HSIs, where these black cells indicate oyster presence at these different sites. Then framing the decision problem as a maximum set coverage problem, what we look to do is maximize our HSI values subject to budget and connectivity constraints. And I do this using linear integer programming. Here I have a budget of 150 sites, which is roughly 1% of the total sites, and each site has an equal cost. Essentially saying choose the 150 best sites based off this HSI values. I then incorporate a directional connectivity constraint based on occupancy of immediately adjacent sites. Don't worry, I have a slide explaining what that means. So here, if we consider the black cell to be an occupied site and say we want to choose this green site, traditionally what we do is we just restore that green site, call it a day. However, if we want to make sure that we're connected to the existing occupied sites, we first need to consider the immediately adjacent sites. We can restore that one, which opens up these ones, which restores that one. And now we kind of have a chain connecting our occupied sites to our site that we wanted to choose. Of course, based on your budget, you're going to choose different sites, and there's a bunch of different paths, which is why we use linear integer programming to do this process. What that ends up looking like for a connectivity constraint of the actual system is as we moved out from these white cells, which are occupied sites, you can see that it gets lighter, which indicates the amount of cells that you need to choose in each layer to kind of move through the landscape. So looking back at our decision problem, what we're going to do is maximize our habitat suitability value, subject to our cost and our directional connectivity constraints. Here's what the final product looks like. So we have the black cells, which are occupied. Green indicates that both frameworks recommended those sites when using them to optimize. Blue indicates that we restore using the Monte Carlo simulation, and yellow indicates that the standard. And so we see that there is a lot of overlap, primarily in this area right here. However, the Monte Carlo simulation shows sites kind of more northern within the system, and the standard methodology shows these sites more southern. And so all of that to say that, yes, incorporating uncertainty may change your overall decision process. However, this is just a very simple example of how you can apply that uncertainty. And so further work really is needed to ground truth these results and maybe do some adaptive management to see how a restoration would perform in these areas, or to also improve the suitability index model by the addition of more parameters. But we did find differences when we incorporated the uncertainty. Alrighty. And so looking back at the overall conceptual model, the HSI model assumes that if I choose sites that I know in a laboratory setting that these demographic processes work on their own, that it should be a good site, right? We should expect, if we know under what salinity conditions reproduction occurs and growth occurs, survival, mortality, that we place substrate there and individuals colonize, it should persist. In all actuality, these processes are a lot more complex in the actual field. And so the idea was, can we expand the overall modeling process to look at actual field observations of these different processes without, once again, modeling them individually? That's how we get into the third chapter. The idea behind this one is integrating prior restoration outcomes within the future restoration planning. And so to do this, what would we need to know? Well, first, we need to know our previous restoration outcomes. We need to know how restored oyster reefs within the area performed following restoration activities. Additionally, we need to know metrics that indicate performance across Swanee Sound, biological metrics such as oyster density or counts, as well as environmental metrics that could impact our biology, such as salinity in our case, as well as many others. Well, here's the oyster density from the Lone Cabbage Reef restoration. You can see 1, 2, 3, 4, 5 years post-restoration, the different sampling efforts within the area, showing that we do have information on oyster densities. Additionally, we have that salinity data from before, right? Spatially interpolated to a 1 hectare scale. As mentioned, there is going to be some model error, but without exhaustive sampling, this is really the best we're going to get. And so what quantitative framework could we use to incorporate these observations of density and salinity, as well as the temporal and spatial aspects? Here I use a geo-additive model. For those of you unfamiliar, it's a general additive model with the tensor product for spatial coordinates. It's basically a quantitative method for relating oyster density to abiotic, temporal, and spatial factors. What this will do is produce a spatially explicit estimates for our oyster densities based off of our restoration data. And we can then use it as a predictive tool to tell us how these different sites would have performed under these restoration conditions. The main concern is the large data requirements. The introduction of the tensor product for the spatial coordinates adds a lot of parameters that need to be estimated. And so within Swanee Sound, we have the question of, do we actually have enough information within Swanee Sound to parameterize this model? So this chapter was a simulation-based study. What I looked to do was generate a test data set, see how much of that data set is needed to provide precise estimates. The test data set was simulating oyster densities using the existing salinity information that we have, and then doing different sampling protocols across the reef system itself at different levels of sampling effort. Then fit a geo-additive model to these sampled and simulated densities and investigate changes in model precision. So for the sampling protocols, there were 2 main questions. The first was, do we need to resolve the data temporally and spatially? Do we need sampling protocols that incorporate the temporal and spatial aspects of the post-restoration responses, as well as how does model precision change as sampling effort changes? As we add more, as we reduce the sampling effort, is there some level in which our error just spikes, or is it just kind of consistent sampling error, sampling bias? And so the first sampling protocol I used was the real-world Lone Cabbage Reef restoration sampling protocol, described in Moore and Pine 2021, but essentially is based on a stratified approach with 23 reef elements grouped into 4 strata. These strata were based off of harvest, no harvest, and then restoration, no restoration, sampled using line transects, and followed an adaptive sampling approach. And those are the data I showed you earlier. Important to note that the adaptive sampling approach did vary sampling effort between each time period. So different number of sites were sampled at each time period, as well as the strata were not inherently spatially explicit. So you may not end up with equal spatial coverage across the reef. I then simulated some sampling methods to kind of answer this first question about resolving the data temporally and spatially. And so first I started with all of the data. Here's what that looks like for the sites that were available. I then incorporated the temporal aspect by doing a repeated measures or a random sampling. Repeated measures at time 1, the sites were chosen and the same sites were sampled at each time period, versus a random at each time period, different sites were sampled. I then included a spatial aspect, either being stratified or random. For the strata here, I created 4 strata to ensure equal spatial coverage, and these went north to south with an equal number of sites in each strata. That's what that looks like here. So we end up with strata 1, 2, 3, 4. And so basically, depending on the level of sampling effort, an equal number of sites were chosen in each site and within each strata if the sampling protocol was stratified. Finally, I varied the sample size, increasing incrementally from 20, 40, 60 to 80% of the full data set. And so the idea here was, if I can create a simulation that represents simple post-restoration dynamics using the available spatial scale and the available environmental data that we have for Lone Cabbage, can I get that model to fit? If I can get that model to fit, at what level of sampling effort do I need? Because in all actuality, the actual post-restoration response of the Lone Cabbage Reef is much more dynamic than what was used in the simulation. So this represents a very simple case to see if this model would work. And so for the modeling protocol, I simulated oyster density as a relationship to environmental variables using a Tweedy distribution. I then fit a model to the simulated data. Here I used, this is for the latent spatial effects, the log of the mean density, the linear and quadratic terms for the salinity, and then a fixed effect for time. And then it was done with a Tweedy distribution. For each protocol and sample size, I did 15,000 replications. And then I graphically investigate variability and then calculated absolute relative bias. So we're going to go through some plots that all look really similar, so bear with me. So this is for the repeated measures stratified sampling. Each panel indicates a different parameter within our model. As we move up the y-axis of an individual panel, that indicates increasing sample size, and then the red line indicates the true value used in the simulation. And so what we can see is that across all of our different parameters for the repeated measures stratified sampling protocol, as we increase sampling effort to around 60%, we get the same amount of variability around our estimates. Similarly, when we do repeated measures random, we see that same pattern as we move up to 60% with the 20% sampling error, 20% sampling effort having the largest amount of variability. Similarly, for the random stratified, we see the same pattern. And then finally, for the random sampling protocol, we see the highest level of variability at these lower sampling efforts. However, as we move up to that 60 to 100%, we see similar variability around our estimates. Then looking at the absolute relative bias, which is the average difference between our model estimates from our simulations and the true value divided by the true value to give us a percent difference. Basically, lower numbers are good, higher numbers are bad. And so we see that at 20% sampling effort across all of our parameters, there is separation between the different sampling protocols. However, as we increase to 40, 60%, they all seem to converge, indicating that we don't necessarily see increased model precision from the different sampling protocols as we increase our sampling effort, at least for the sample size we have here. Additionally, we find that the Lone Cabbage Reef restoration sampling protocol has higher sampling error than the 40% sampling effort protocol, which indicates that there is some need to account for the temporal and spatial aspects of the restoration response because the Lone Cabbage Reef did not, and therefore we end up with this higher bias within our simulations. Additionally, we find at the 100% sampling effort that we still get, for some of the parameters, we get relatively high bias. For some like salinity, we end up with around 1%. However, for the temporal effect of occasion 1, we get 7 or 8%, and that varies across our different parameters, indicating that even at 100% sampling effort, we're not getting great precision of these models, indicating that at the spatial scale with the number of sites we have to sample, this model is not going to work. And so overall closing remarks, you've stayed with me this whole time. The first chapter showed that restored oyster reefs in Swanee Sound may provide freshwater detention near the river mouth. This is going to be a function of the discharge levels as well as reef proximity. However, these information on this is still relatively unknown. And so future monitoring efforts really need to look to evaluate the relationships of these. The Lone Cabbage Reef restoration had very high temporal resolution, but very low spatial resolution, or very low spatial coverage, whereas other works in the area had very high spatial coverage, but very low temporal coverage. So some sampling monitoring efforts in the middle may help shed some light on this hypothesis. Additionally, the second chapter showed that Monte Carlo simulation could work for incorporating habitat metric uncertainty in these HSI models. We should look at the addition of more habitat metrics and how that plays a role. Primarily salinity was the main driver within our models, as we saw temperature is fairly homogeneous across the region. So as we add in more variables, and you may get different dynamics to see how that uncertainty kind of propagates. Additionally, larval transport was fairly simple here. It was just assuming if you're next to an occupied site, you'll become occupied. Realistically, you need to consider the overall hydrodynamics of the system to see how exactly larval transport may occur. And finally, the third chapter showed that it could provide a framework for integrating restoration outcomes in the future site selection process. But within Swanee Sound, we have some spatial resolution problems that unfortunately means this model is not going to work there. We could do some future simulation work to kind of work out what spatial scale we need to collect this abiotic and biotic data to make it work. as well as develop monitoring protocols so that you can improve your spatial resolution of your abiotic factors so that you can increase the spatial resolution of your biotic sampling as well, somewhere in between there. And that's all. So I'd like to thank National Fish and Wildlife Foundation, UF, as well as USGS for their help throughout this process. And with that, I'll take any questions.
Hi, really great presentation. I liked it a lot. I did my master's in Louisiana on oyster reefs.
Mhm.
And I looked at kind of the biodiversity and one of the key things I thought was missing in your concept map was predation. And I was
Yeah.
wondering how you accounted for that, what your thoughts were, because you know, there's plenty of predators on oysters and also the spat.
Yeah, so predators are something we don't really account for within this context. Swanee Sound is a very data poor. As you can tell, I only use salinity and temperature. There's a lot more information that would need to be included, including predation, but also food availability, dissolved oxygen content, bathymetry. There's a lot more there. I'd love to include information on it, and there are some people within the area kind of adding to that overall data knowledge, but at the time didn't really have access to it. Might be a chat. Do I read out the chat or do I just answer it?
You can, just, I guess, either one, whichever is clear to everybody, I guess.
Okay, sorry, I have to read it. Let's see. I guess I'll read it for the people here if they don't see it. Of the most important lessons you've learned about adaptive management protocols, what 1 to 2 do you most hope practitioners will take away from your work? I.e. the importance of evaluating different frameworks, the importance of incorporating on connectivity, etc. Sorry, it's a long question. Yeah, I think when considering these adaptive management protocols, it's really important to think about the scale of the effort you're doing and then make sure that you're monitoring it in a consistent way. So with Lone Cabbage Reef Restoration, there was that pilot project, which really looked at, okay, if we place this substrate there, will we see colonization, right? Will we see individuals persist at these sites? Then at the larger scale restoration, we've kind of followed similar objectives, seeing how if we add a more additional restoration effort, do we still see that restoration outcome? And so I think staying consistent along the way that you measure restoration success and really your goals, even as you move through the process, can be helpful. Additionally, I think in the context of, say, my second chapter where I mentioned it, these site selection processes are really not the ultimate tool, right? I can't take this to managers and just give it to them and say, here's where you restore, right? It's a decision support tool, which is better than them having no information on the system. It helps kind of guide their thinking to say, these may be sites that could work, however, we need more information. And so kind of setting up the groundwork so they're not starting from zero. And here is kind of a place to start, and you can introduce some small scale efforts within those areas to see how the overall model predicts those areas, as well as how restoration may perform and what more additional information you may need for making future restoration decisions.
Sorry, I have another question.
Go for it.
What are your thoughts about including live oysters in initial restoration efforts? You know what I mean? Like actually just.
Yeah. So in a lot of places, they'll place like in Lone Cabbage, we use limestone rock, and then you do some shelling, which kind of creates that overall initial habitat matrix. It's kind of challenging. It's expensive, first of all, to add those in there. And in restoration, you're trying to really get the most bang for your buck. If it depends, because depending on the site conditions, you may have high reproduction, which may help like kind of contribute to that oyster stock at that site. But I guess it really depends on how many you're adding and the cost benefit analysis of, okay, if I add oysters here, that means I can't put rock here. So it's kind of like a trade-off, but some places have shown success with it. Some places have not shown success with it. With it, and so it really depends. At least in Lone Cabbage, it was just the limestone rock with shell on top. Here's another chat. Anyone else here? Okay.
All right, does anybody have any other questions?
I'm wondering why you chose a random forest model and what other alternatives you considered.
Yeah, that's a great question. So I kind of tried the whole suite. So I did a neural network, support vector machine. So here I used the random forest, which is bagging decision tree methodology. I also used boosted regression trees to kind of explore the problem. What I found that the random forest really helped with those kind of fluctuations within a daily cycle. So I was trying my best to avoid including a temporal aspect, because if you include some time lag or something like that, you lose a lot of inference on the other impacts of the different variables. And so I was able to get almost 100%, 1.0 R squared if I used a recurrent neural network and a long short-term memory neural network, which included a lag for salinity. But then I lost all information on my other variables. Similar with the boosted regression tree, I ended up losing a lot of information on what exactly was driving my models. And so the random forest was the one that fit best and was able to account for those random fluctuations during short time periods. Because realistically here, within that first chapter, I included discharge, temperature, wind, and tide, but I didn't include anything about surface runoff or groundwater inputs. Or precipitation itself. So there's a lot of information that's being left out. So you could see random fluctuations in the salinity that may not be explained. However, the random forest is really great at seeing those kind of cutoffs and adjusting your prediction for them. So that's why I tried everything, if I'm being honest, but the random forest seemed to fit best. Interactions is a tough one. I mainly just looked at so what exactly do you mean by interactions? Yeah. So as far as within the machine learning algorithms, I just put them in as input layers. I didn't do any complex. I didn't use like a deep learning model, which kind of combined the different impacts of the different variables. So it doesn't really look at any interactions from a statistical standpoint. However, it does kind of look at the overall parameter space. So like if you think of like two variables, it's looking at a plane and how your salinity changes across that plane. Of course, when you have these 5 or 6 different variables, it becomes kind of hard to conceptualize, but kind of moving through that parameter space. And so there is some interaction of the different variables, especially within a random forest, how you have like the different trees. A random forest is just a bunch of decision trees kind of ensembled together. So within the decision trees, you're kind of moving at each node. And so you may have one based off of temperature and then one based off of discharge. So as you move through your decision tree, there may be some interaction between your different variables, but from the model formulation, no, I didn't consider like interactions within that aspect, but the model kind of does it for you. Sorry if that was an over explanation.
So there we go. All right, any other questions on Zoom? Looking at the chat and I'm not seeing anything. Okay. All right. Well, thank you very much. That was lovely, very interesting. And so for everybody in the room, just make sure that if you are registered, just a reminder to sign the little sign-in sheet. Otherwise, if you have questions or concerns, let me know. And I will see you guys next week. Thank you. Thank you very much.
Thank you. How do I do this? Do I just stop share?
Yeah.
Good job, Matt.
Thanks, Bill.
Give me a call later when you're on your way back or something, okay?